Okay, we are back and we're going to start in, I think is usually one of the most exciting areas right now, which is POCS, alternating projection onto convex sets. So I am going to share my screen and too many screens open, guys. I have too many screens open. Share the screen, share the screen, share. Okay, and too many things to click. So POCS is, as you can see here, it's a tool for signal synthesis and analysis. And you'll find out it works in a lot of places very well. And if it doesn't apply to a specific area, you don't want to use it. We're going to be showing it for a number of different applications. POCS stands for alternating projection onto convex sets. You might wonder where the alternating went to. I don't know. It's just always been POCS. So it's alternating. That was left out, projection onto convex sets. So what I want to do, first of all, is paint an intuitive picture for what happens with POCS. So let's go ahead and start. In a vector space, and this could be like a two-dimensional or even a three-dimensional space, a set is convex if and only if, for every x in C and y in C, then this linear combination is in C for all lambda is between 0 and 1. You look at this, and unless you sit down and digest it for a while, you kind of go, blah, blah, what does this mean? Let me give you a geometric interpretation of what this means. What this means is as follows. If we have, by the way, I should probably go full screen here because I think there's some animation in here somewhere. Okay, I guess not here. So here's the idea. You have this set which is convex, and the set which is convex here is the is this purple one, right? And it's in this oval. And what this says, if I choose a point X in this set, and I choose a Y in this set, and I connect a line segment between X and Y, that line is totally contained in the convex set. That's all that this stuff up here means. If I connect these 2 points, the line segment connecting them. And this is actually an equation of a line connecting 2 vectors. Notice lambda is between 0 and 1. What happens when lambda is equal to 1? What is that equal to? If lambda is equal to 1, this is equal to x, isn't it? Right? So here is lambda is equal to 1, that's x. What about lambda is equal to 0? If lambda is equal to 0, then the value is y. So up here, the value y is lambda is equal to 0. If lambda is equal to a half, what do we get? We get the average between the 2 vectors, correct? We get the average between the 2 vectors, and this average lies right here, right? So that's lambda is equal to a half. So as lambda increases, we see that this line segment starts up here at y and works down all the way to x because lambda is only allowed to go from 0 to 1. So that's the definition of a convex set, at least geometrically. Well, this is the mathematical definition. This is an interpretation in 2 dimensions of exactly what this means. And I think it's probably easier to think about this in terms of the geometry, although we will return to this definition when it suits us. So here are things which are convex sets. This is a convex set. No matter what 2 points you choose in this set, if you connect the 2 points, they're going to be totally in the convex set, right? Here is something which is interesting. A line segment is a convex set. Because if we choose this point and we choose this point and we connect the 2 points, then that line is totally within the convex set, right? So a line segment is a convex set. This is a convex set. All of these are convex sets. The generalization of a line to a plane is also a convex set. So here, if we choose a value of x and y, and we connect x to y, we're still in the plane. That entire line segment is totally subsumed in the plane, right? all of these are two-dimensional examples, and three-dimensional, a sphere, for example, is a convex set. The cylinder is a convex set, because I don't care where you choose a value of x and y within the cylinder. If you connect the line segment connecting x and y, then that line segment is totally going to be within the set. So some sets which are not convex are shown on the bottom. You can see this star. You only have to have one example that violates the criterion. So we choose this point, and the line segment lies outside of the set, so it's not convex. The donut here in the middle is not convex, because if we choose 2 points appropriately, the line segment is going to go through the hole in the donut, which is not a member of the convex set. And also this crescent moon over here is not convex, because if we choose a point here and a point here and we connect a line, we see that the line segment is external to the moon. We good? So that's the definition of the convex set and the geometrical interpretation of this in 2 and 3 dimensions. We want to extend this to higher dimensions, and we'll see how we do that very, very, very soon. Here is an example of a signal. There are so many signal classes that turn out to be convex. One is the set of bounded signals. Now, what is a bounded signal here? Well, a bounded signal, the way we've defined it, is a signal that is totally contained in the interval from -u to u. That's what this is. So x sub n, all x sub n's, all values of the function lie between a lower limit and an upper limit. I guess I didn't do that here though, did I? Okay, so all of the elements lie between 0 and u. I put this -u here, I shouldn't have done that. All of the elements lie between 0 and u. So this is a bounded signal because all elements are in this interval, correct? Now I have here a very, very simple signal. I only have 3 elements in the signal. Why do I only have 3 elements in the signal? Because that allows me to draw a 3-dimensional picture of what this means. This is a set, this is the set of all signals which are bounded. You'll notice this box goes from 0 to u, 0 to u. U, by the way, is not a frequency here. It's just a number. The U stands for upper bound. And so if a signal is bounded, then it lies within this box, doesn't it? And in fact, this signal, which is, I don't know, here, here, and here, might be a point right here that lies within the box. If a signal is external to the box, external to the box, for example, out here, that means that x1 is greater than right here. If we looked at that point, that would mean that x sub 1 is greater than u, right? And that would not be a bounded signal. So everything has to lie inside the box. So we want to take the set of all bounded signals. I've illustrated it for 3 signals, but this goes up to 20 signals, 5 billion signals, an infinite number of signals. It's all a box in a higher dimension, and it turns out to be something which is convex. And here, for example, is a continuous signal. Here we have a continuous signal, and this signal, we've kind of redefined it. It's between a lower bound and an upper bound. Okay, so x of t is the set of all signals lying between a lower bound and an upper bound. And so in a higher dimensional space, this would correspond also to a box, which is shown down here on the bottom. It is a convex set. And here we can prove it. Now, to prove it, we have to go back to the definition of the convex set. We have a bounded signal x of t. We have another bounded signal y of t. If we add lambda times x of t plus 1 minus lambda times y of t, and lambda is between 0 and 1, is that signal bounded also? Yeah, I think it is. For example, if we have this signal,
Did you say lambda is between L and U or 0 and 1?
oh, did I say that wrong? That's what I meant. Lambda's between 0 and 1. So here we have two signals. Say this is y of t. If I had, for example, lambda is equal to a half, what would that be? That would be the average of these signals, right? The average of these signals would kind of look like this, wouldn't it? So this would be 1/2 x plus 1/2 y. It'd be the average between the two signals. And is that signal bounded for lambda is equal to a half? Yeah, it's bounded. And in fact, as lambda goes from 0 and 1, you're going to go between the lower signal for, what is this lower signal? X of t, that corresponds to lambda is equal to 1. The upper signal, which is y of t, is lambda is equal to 0. And all other signals are going to be between these two signals, and it's going to be a bounded signal. So yeah, this is the proof of our intuition that the set of all bounded signals is itself bounded. Let's look at another example, identical middles. Here what we're going to do is we're going to require that one of the samples always be 1. We're going to require that this sample be 1. And say we had another signal and say this signal was this, and 1. So all of the signals in the convex set must be equal to 1. All the signals in the convex set must be equal to 1 at the third entry. Does that make sense? So if we had another signal, we can have another signal here, I don't know, way down here, and the third signal has to be 1. All of the signals has to be 1. All of the values have to be 1. The set of all signals where the third value in the signal is always 1 also forms a convex set. So in this example, the convex set is all x sub n in 3 dimensions where the third element is equal to 1. That's the convex set. And what does that correspond to? Well, in 3 dimensions, this is something we can draw. We can go out here to x3 and look at this plane. This plane is x sub 3 is equal to 1. That's what this plane is equal to, correct? And we've already seen that a plane is an example of a convex set. So this is another example of a convex set. We can extend this to higher dimensions and say, for example, all signals, and this is where the identical middles comes in, all signals that look like this in the middle form a convex set. So I don't care what it does in the tails. I only want it in the interval. I want x of t to be equal to some sort of constant in the middle. And I don't care what it does in the tails. So you notice here, x of t is this and y of t is this one. And both of them look exactly the same on the interval. I think that's a script I or something like that. The tails are different. The tails are different. But all of the signals in this set turn out to be a convex set where all of the signals are identically equal to a specified function within a specified interval. Because if we take lambda times this, lambda times the constant, and then down here we take 1 minus lambda times the constant. As long as we're in this interval, lambda times the constant plus 1 minus lambda times the constant, it's always equal to the constant, right? We always get the same thing back. Now the tails are going to differ as we do these different combinations. As lambda varies, the tails are going to be different, but the middles are going to remain exactly the same.
Dr. Marks?
Yes.
So in this case, the signal x of t and y of t are the set, right?
These are two examples of these are two examples of elements that belong to this set.
Yeah, okay.
Okay, it doesn't define the set, they're examples. There's an infinite number of elements in the convex set, but these are two examples that are in this convex set. Here's a fixed area signal. What do I mean by a fixed area signal? Well, here I mean that all of the signals where x sub 1, x sub 2, and x sub 3 add up to a specific area. Okay? You can think of this as kind of the integral. The integral of x sub n is equal to a constant, and this constant remains the same. If you fix the constant and look at the set of all signals that this corresponds to, this is also a convex set. And we can visualize this by looking at things in 3 dimensions. This is the plane which is defined by x1 plus x2 plus x3 is equal to a. You will notice that if x1 and x2 are equal to 0, then x sub 3 has to be equal to a in order to give it an overall area of a, right? In a similar fashion, if x2 and x3 are equal to a, then x sub 1 has to be equal to a. What's the value right here in the middle? That would be like 1/3. 1/3, 1/3 plus 1/3 plus 1/3. Each one would be 1/3. This function sometimes is called a simplex. And you'll notice it's something which is used in probability. Well, first of all, before we go, you can see that this is a plane. It doesn't go through the origin, but it is a plane, and therefore we've decided that it is a convex set. It's a simplex because if we have a probability density function, well, let's see. If we have a probability density function, p sub 1 plus p sub 2 plus p sub 3, if you're into probability and you have 3 possible outcomes, what does the probability of all 3 outcomes have to add up to? It has to add up to 1, doesn't it? That's the idea of a probability distribution. All of the probabilities have to add up to 1. So all probability density functions lie on a simplex because their sum must be equal to 1, whereas we'll see more in general for the continuous case, their integral has to be equal to 1. So here is the generalization of the idea. It's the set of all signals, x of t, such the integral from minus t to t is equal to a specified area. In other words, this area must be equal to a. And there's a whole bunch of signals that can be written there that have an area of a from minus t to t. Do you agree with that? And that does turn out to be, interestingly, a convex set. And it's a convex set. It's a simplex. It's a simplex, and it's the way that we think about things. So here are 2 examples. This x of t has an area of a. This x of t has an area of a. We're assuming it isn't marked here, but this goes from minus t to t. This goes from minus t to t. And in general, we don't care what happens on the outside, right? We're just integrating from minus t to t. And this is really easy to show. This is really easy to show because say we have two functions that have an area of A, and we take lambda times one of the functions plus 1 minus lambda times the other function. This is almost trivial because what's the area of x of t? The area of x of t is A. What's the area of y of t? The area of y of t is A, and so we're just having lambda A plus 1 minus lambda A is equal to A. So if you do this combination of these two signals, you get another signal which is also in the set. So I'm trying to appeal here both intuitively by looking at the lower three-dimensional and also recognizing that we can go to the definition of convexity and in most cases prove very simply that the set corresponds to a convex set. And just like in one dimension, this is a simplex in higher dimensions. This one is kind of obvious. This is when the energy of a signal is less than or equal to some bound. This is fixed. Do you remember how we defined the energy of a signal in discrete space? It was the square, it was a sum of the squares, right? That was the energy of the signal. And I think you can see immediately that this equation forms the equation for what? A ball, right? It's a ball. Everything everything inside this sphere of diameter 2e is within the convex set. And you can see since it does, this ball that I've written is generated for the equality here. So that's the surface of the ball. But anything inside the set is also bounded by this less than or equal to. So this one is just geometrically obvious since we have a sphere, right? So that corresponds to a convex set. So we see that we have convex sets everywhere. It's kind of cool. Convex sets are ubiquitous. I mean, we've done a lot of stuff here. And here is the generalization to continuous time. It's when the, do you remember this definition of x of t squared? That's equal to this norm squared. So it's that this integral is always less than or equal to e. And that corresponds to a ball, and that is something which is convex. Kind of cool. Lots of things form a convex set, right? Lots of signal classes form a convex set.
Yeah. So did the previous slide show a set with like 3 parts of it fall inside a ball, and the next one that we just looked at is the whole thing is inside a ball?
Yeah, well, it's first of all, it's an infinite dimensional space, right? So yeah, everything is inside the ball in this very high dimensional space. And it's something we can prove. We can prove by going to the definition of the convexity of the convexity definition, and we can prove it. And here it is. If you'd like to go through it, you're welcome to. But we use something which I hope you've heard of before. It's something called the triangle inequality. And the triangle inequality can be shown that this is indeed a convex set if we follow the definition of convexity that we originally gave. And clearly, geometrically, if we have a ball and we choose any 2 points on or in the ball and we connect a line segment, that's going to be totally subsumed or included in the ball. Here's one that's interesting. The set of all band-limited signals. This is where we get into the Fourier analysis. And by the way, this is in one dimension. This extends to higher dimensions. It's that x of t as a Fourier transform of x of u. And the Fourier transform, by our definition of band limited, is only zero. It's always zero outside of an interval from minus b to b. By the way, our definition of band limited is very idealized. You never in practice find something which is strict. Well, you do. You do find things which are strictly band limited. But in nature, usually you don't. Many times we say something is band limited if the amount of energy outside the band is negligible. But for our purposes, we're going to have it exactly equal to minus b to b. By the way, how can we force a signal or an image to be zero outside of minus b to b? We take a Fourier transform, we chop off all the higher frequencies, and then we inverse transform. So you can do this for images, right? You can use an image. You can take a 2-dimensional FFT. You can just block out where you want the signal to be band limited, get rid of all the higher frequencies, and just inverse FFT it. So in that sense, it does exist. So here's the point. If x of t is band limited and y of t is band limited, is the combination of x and y band limited? It's almost intuitively obvious, I hope it is, that if y of t is also band limited, then lambda times x of t plus 1 minus lambda y of t is also band limited. Notice that lambda t, x of t, plus 1 minus lambda of y of t Fourier transforms to what? By the linearity of the Fourier transform. And so this is something which we call z sub u. Now clearly, if y of u is zero outside the interval, and I'm sorry, x of u is zero outside of the interval, and y of u is zero outside of the bandwidth interval, then z of u, adding them together, is going to be zero outside of the band limited interval. That's kind of obvious. Well, this is zt, right? So we've just derived z of u, and z of u is obviously is going to be zero outside of the interval. So z of t must, by definition, by necessity, also be band limited. So wow, we see that we have a lot of convex signals, signal classes, if you will. These are classes of signals. Let's see if we have another example of a class of signals. This is, yeah, very interesting. This we get in tomography. And here I'm not going to do a projection, but I'm just going to do a projection on a line. So here's what I'm going to do. I have an image, and I'm going to do the projection on a line. And what does that projection on the line mean? It means that I take a one-dimensional function along this line as it slices through the image, and I'm going to take the area of it, and this area is going to be equal to p, right? Now I'm going to look at another image. I don't know, some other strange image here. I'll look at some other image and I will take along the same exact line, the integral here. It's going to be a different function here. But I'm going to assume that this area under this new signal is also P. So I'm looking at the set of all signals or all images that have through this predefined slice an area of P, because that's the projection along a line. Notice that this is kind of the same thing as a constant area, because all of these signals are just the integral of them is the area under that one-dimensional slice, and that has to be equal to P. So for a given P, a given path, P is the path here. If we integrate along this path in one dimension, this two-dimensional function, and we get P, the set of all images, f of x, y, that satisfy this form a convex set. And for those of you that are taking Dr. Schubert's class, there's a procedure in tomography called ART, which makes use of this observation. And we'll see it's a very interesting observation. So yes, just like constant area. Do you remember the constant area, the area from minus t to t of x of t is equal dt is equal to an area? We said that the set of all signals that had this area A formed a convex set. This is exactly the same thing. It's exactly the same thing because we're keeping this path the same and defining our convex set. We don't care what's outside of this path, only along this path. And the set of all signals that give you these one-dimensional slices which integrate to P themselves form a convex set. Any questions on this? We got first of all into a two-dimensional example. So yeah, here is the same example that I gave before. Here is f1 of x. This is the image of the brain, and here's f sub 2 of x, which is it's a guy with a pretty bad brain disease, I guess here. And we take the area over this predefined P here, and we take the area under this one. And if both of these images gave the same exact area P in this one-dimensional slice, then we say that this is a convex set. And this convex set is parameterized by P. If I choose a different P, I get a different convex set. But for this one, we're just assuming that P is fixed. And the proof is exactly the same as the set of all signals with the same area. It's exactly the same. Lambda times f1 over the path P plus 1 minus lambda, the integral over f sub 2. Well, it's equal to lambda P plus 1 minus lambda P. Both of them are assumed to give you an area of P. And so therefore we get a convex set. So just like the area, the constant area case, the set of all signals that satisfy this property forms a plane. I think it's very interesting in most of these projections, or in most of these cases, we can literally determine the shape of the convex set. For example, the finite energy was a ball. The set of constant area was a simplex, right? Which is that plane that cuts through the first quadrant, but it extends beyond. So we saw that the set of all bounded signals corresponds to a box. So all of these signals suggest a corresponding geometric interpretation that we can use intuitively to figure out what happens in higher dimensions. So, all well and good. We're going to ask ourselves now, what is a projection onto a convex set? Because POCS is projection onto a convex set. You're going to find this very interesting. For every closed convex set, what does closed convex set here mean? Well, closed is a fancy word that mathematicians use, but for our purposes, a convex set that is closed is a convex set that contains its skin, right? That contains its skin. What do I mean by that? You could talk about a ball, for example, and you could say all of the signals where x of t is less than or equal to some bound E, so that would be the energy of the ball. But another convex set would be the set of all signals that are strictly less than E. Notice the equality here doesn't have the inequality doesn't have an equal sign accompanying it. So that's what I mean. This one contains its skin because it contains the surface of the convex set. This is still a convex set, but it doesn't include the surface of the convex set. So a closed convex set is a set that is, the skin is totally on it. Now, I think in engineering applications, we really don't care about this, but it's something that is nitpicky for the mathematicians. Here's the interesting part. If we have a closed convex set, there's a vector in a Hilbert space, and a Hilbert space is just a multidimensional space. It can have actually up to an infinite number of dimensions. There is a unique vector in C closest to X. This is very interesting. What does this mean? This means that if we have a convex set here, which is C, this C is shown as the yellow, and we have a vector external to the convex set, there is a unique point in the convex set to which this point is closest to. There's lots of other points in the convex set, but all of these points are further away than this projection. This projection is the unique point that is closest to any external value. And we see that this applies to a number of places. If we were to choose our X out here, what's the projection? The projection onto the convex set is here. We denote that projection by a subscript C. So this point is referred to as the projection onto the convex C of the vector X. And it is also a point in the higher dimensional space. Every value of X here has a unique point in the convex set to which is its closest. We're going to state this without proof. I think geometrically, it's kind of obvious that that's the case, right? For every value of X, you're going to have a unique point which is closest to X that lies in the convex set. Now, if we change the point, we change its projection. So different points are going to have different projections. That's fine. And here's the interesting part. Say we're already in the convex set. Say that there's a point Z that's already in the convex set. What is the point in the convex set that's closest to Z? Well, the point in the set which is closest to Z is Z, right? So this is the projection onto the convex set of Z, if Z is already in the convex set, is equal to Z. You don't move at all. You are at the closest point within the set. Here's a fancy word. Idempotent. I like that. That's a word you can impress people with. The projection is idempotent. Idempotent is, if you do it twice, it's the same as doing it once. So if you project onto a convex set, and then you take this point and you project onto the convex set again, you don't move. I use the example, it's like sweeping all the dirt off a floor. If you sweep all the dirt off a floor and then you go back and you sweep all the dirt off a floor again and you did a good job the first time, that's an example of an idempotent operation because you've done it twice and you get the same results as if you did it only once. So idempotent is idempotent is a property of a projection onto a convex set. So let's take a look at some examples, revisiting the convex sets that we've already seen. Look at some examples of projections onto convex sets. Say, for example, I had the case of x sub n is equal to 0, and I'm sorry, x sub n, the signal x sub n lies between 0 and u. It lies between 0 and u. Well, here is an example of a case that doesn't lie between 0 and u. This is this point, which is greater than u, doesn't allow you to place this signal within the convex set. Well, we've determined before that the set of all bounded signals corresponds to a box, which is shown here on the right. And so what we have is we have a point out here. And which point is off? The first one, right? Y sub 1 is off. And so to project onto the convex set, guess what we do? We set that exactly equal to the upper bound. So we take this point and we make it into this point, and that makes the unbounded signal, or not the unbounded signal, the signal that didn't conform to the bound constraints, it makes it now conform to the bound constraints. Notice what that does in the three-dimensional space. Here is our point, which is not into the set. We're taking this value, x sub 1, y sub 1, right? We're taking y sub 1 and reducing y sub 1 to where it's just within the bounded state. Notice that's exactly the same thing as projecting it onto the surface of the box. So that is an example of a projection onto a convex set. That's how we do it. That's a projection onto the set of bounded signals. How do we extend this to continuous time signals? Suppose that we have a signal which is band limited between a lower value and an upper value, and this signal is not band limited. It is not band limited. The set of signals which corresponds to the convex set requires that the signal be limited between a lower value and an upper value. It is very clear here that this signal extends beyond these limits and is not a member of the set. So what did we do in the previous case? We just took the samples that exceeded the bounds and we just kind of clamped them down. These projections are very intuitive. And what do we get here? We get this. See, before this signal went up like this. So we just took this signal and we just clamped it down so that it conformed to the boundaries, to the lower versus the upper, right? And we did this also for the negative part. We just took the values here. So if you take a signal which you want to be bounded and you want to project it onto the convex set of bounded signals that obey this constraint, you simply clip the signals off at the upper and the lower values. Again, I would submit to you that this is a very, very intuitive sort of way to do a projection. And just like in the three-dimensional case that we considered, we can always think of this as a projection of y of t onto a box, except this box is in a very high dimensional space. It's in a very high dimensional space. And something that we can't visualize, but we can visualize it in 2 and 3 dimensions, and that helps us to understand what is happening here. So we project it onto a box. What about identical middles? Here's an example of the set of signals, and remember we wanted to set the third element here. We wanted to set the third element here always equal to 1. Well, here's an example where the third element in the signal is not equal to 1. How do we project onto the convex set? I think now you can probably guess that we project onto the convex set by requiring that third signal equal to 1. I mean, it's obvious, kind of intuitive, isn't it? And what does that mean in terms of the box? If you remember, the set of identical middles in the set of all signals that the third element was equal to 1 correspond to this plane, right? Corresponds to this plane. So if we had a point closest to it, we would imagine that the projection would be onto the plane. And that's exactly what we're seeing here. It's a projection onto the plane, and that plane is that point on the plane, which is the projection of this point to the convex set, is the closest point in the plane. If you're external to a plane and you want to find the closest point in the plane, you just drop an orthogonal projection, right? And that's exactly what we've done. So this is the example that we have. Again, in order to project, we take this value and make it the identical middle in order to make it conform to the convex set. And that's just like taking this signal and projecting it onto the plane. And so this is the projection onto the convex set. This is the convex set. Projection onto the convex set of the vector y. Okay, let's go on. All of these are pretty intuitive, aren't they? The idea of the convexity and the idea, I hope they're intuitive, the idea of the convexity and the projection onto the plane. So here is an example. Remember we had this function which was C of t here? This was the continuous version of identical middles. All of the signals that look like this little humpy thing here. Well, suppose we have a signal that doesn't look like this little C of t in here. Okay, we have this signal which is shown. How do we project onto the convex set? Well, it's very simple. We just throw this part away and we stick in C of t there, the middle part, and that is the projection onto the convex set of identical middles. And this will now fit in the convex set as we've defined it here. And just like in the example that I gave you for 3 dimensions, this is like taking y of t and projecting it onto the plane that corresponds to the identical middles. Here's a little bit, this is a little bit more tricky. Any questions so far? This is pretty clear, and I hope that the geometry is making things clear. Suppose we have a constant area. This is a little bit weird. Suppose that we had x sub 1. We wanted to look at the case where this sample plus this sample always added up to 1. You can see here that this sample plus this sample add up to 3. So that's not in the convex set. So our convex set is when the first sample plus the second sample adds to 1. Correct? Well, here's the situation. Here is the point which is external to the convex set. Which point in the plane is closest? It's clearly going to be that point, but how do we get from this point to this point? We do it by we do it by something interesting. Notice that from getting to this point, since this is a 45-degree line, this is a 45-degree line, right? We have to subtract off the same amount in x1 as we do in x2. I don't know why I have the y. This should be a y1. We have to sample out, we have to subtract off the same value here as we do here in order to get to the point. So this is the key. We have to subtract off this, and we have to subtract off this, and the amount that we subtract off from both cases has to be exactly the same. Let me give you a hopefully a nice interpretation of this. Say we have an x of t, and this x of t is supposed to have an area of A, but it doesn't have an area of A. We want to subtract off the same amount in every case. So what we're going to do in order to do this projection, all of the points have to be subtracted off exactly the same. So it means that we keep exactly the same shape as the original function. I'm trying to reproduce this shape. And we can think of it as just reducing this thing down to a point where it has an area of A.
And
so go ahead, David.
So this line being at 45 degrees is because there's nothing about any of the points being weighted more than others?
Yes, if we weighted these points more, which would also be a convex set, then this would be not a 45-degree line. And that's another problem, but you're totally correct. So I like to think of this as this is the way I visualize it. I think of this thing as an iceberg that's floating on water. And what you have to do is you have to reduce the water, the height of the water down so that you get the proper area. So we have kind of the function floating on the water. So we take the whole function and we reduce the water level, and the whole function comes down. The whole function comes down, and it comes down to the point where it finally has the area of A, and that is the projection. Kind of cool, huh? So again, this is explained at this point. It says the same value in this example 1 is subtracted or added to every value. So if we take this value, notice that this is exactly what we have. And we're going to lower the water level. We're going to lower the water level so that this becomes 1 and this becomes 0. Is that okay? Do you see the idea of reducing the water level? And so if we reduce the water level by the same exact amount, we get that, yes, it's, this becomes, okay, I don't know why I have this labeled this way. This should be 0 and 1, right? It is reduced to a value of 1. So that now the new values at this and this add up to what? 1, right? So again, constant area, I like to think of it as just reducing the water level. Now, sometimes the signal might even go negative if you reduce the water level more and more, and that's okay. The signal's allowed to go negative. Okay, so this is the constant area signal, and here's the analogy. You take the projection onto a convex set Y is exactly what I said. It's reducing the water level. And you can look at this equation, if you will, and you can see that this is a reduction of the water level. It is the area of Y It is the area of y minus the area of a, but you have to keep the area of a over a certain interval, say from minus t to t. So whatever that interval is, you have to divide by that in order to keep the area constant. So this is the water analogy of reducing and projecting onto sets that are simplexes, that all of the values sum to be equal to a constant. So here is an example where you have to raise the water level. This signal has an area less than A, so you have to do a filling of the water in order to get it up to an area of A within that interval. I previously talked about lowering the water level. You can also raise the water level if, in fact, the area is too small. So this turns out to be the projection of this signal. It's the projection of this signal onto the set of all signals with a constant area of A. So this is the projection. And it looks like I goofed again. This should be a T. Well, it's amazing all the mistakes you find out when you go through your slides. Okay, so it's the water fill. That's what you need to do to project onto that area. What happens if you have a signal which is not band limited? The answer here is really obvious. You pass it through a low pass filter. That's it. If you have a signal which is not band limited and you want to make it band limited, in other words, you want a function which is 0 outside of the minus bandwidth of the bandwidth, should be magnitude, that is 0 outside of the bandwidth, you just you pass it through a low pass filter with a bandwidth of B. So notice in all these cases, you have what you have, you want to make it into something you want, and it's usually the simplest way to take what you have and make it into what you want. If you have a signal which isn't band limited, you want to make it band limited, well, you pass it through a low pass filter. And that's exactly what the projection is onto the set of all band limited signals. Now, the tomographic projections are the same as the constant area. So if you have a projection which should sum to P and it doesn't sum to P, you need to raise the water level or lower the water level along that projection. That's it. And that is the projection for a given P on that convex set. So here you can see the value here, and the value of P here is too small. So we want to raise the water level, and this is what happens when you raise the water level. You give a little bit of get a little bit of elevation to that projection, and that is the projection onto the convex set of all of the signals which have an area of P. Notice again, this is a convex set which is defined for a specific P. If I chose a different P, a different projection, say in this direction, that would be a different value of P. This would be P, maybe this would be Q, and I would have a different set of convex, I would have a different convex set along this line. So we're being very restrictive here in that this tomographic projection is for a specific path, linear path through the image, which we call P. What about a ball? What about things which have an energy below or equal to a certain threshold? Well, if the energy is already small enough, you leave it alone, right? If the signal is already in the ball, you leave it alone. If it's external in the ball, well, you need to simply scale it so that it has a proper value. So if we have an x of t here, we want to project it onto the ball. And to project it onto the ball, we simply do this result. We do E times y of t over y. The magnitude of y, where y of t is, if y of t is greater than e, this looks like the way to project the signal onto the ball. You'll notice here that if we look at the square root of the energy times y of t divided by y of t, and we want to look at this value squared and integrate over it, that this is equal to, whoops, this should be dt. Can you see this is equal to E? The E sucks out here in the front. What's left on the inside? Well, and also the magnitude of y squared comes out to the front. And then the integral over what's left, this should be a magnitude, by the way. The value that is left inside is y of t squared. And so we can see this is E, and this thing just comes out to y squared over y squared. And that's equal to E. So you've projected yourself onto the ball. You've projected yourself onto the ball. Okay, we're going to talk, and we're just about done with this lecture, but let me give you a little piece of lecture advertisement. This is the promo for the next lecture. If you have two convex sets, here's a convex set C1 and C2. I think you can see that C1 intersected with C2. This is the intersection, right? That's the intersection. That C1 intersected with C2 is going to be this kind of light purple here, and that is also going to be a convex set. So intersections of convex sets are convex sets. This turns out to be useful in many cases. Here's another example. We have a convex set, which is kind of a, okay, I'll check you out here. Is this an oblate or a prolate spheroid? It's hard to tell because we don't have the third dimension. It's a spheroid, and whether it's oblate or prolate depends how it extends out of the screen towards you, whether that's big or small. But we have two convex sets here. We have the spheroid and we have this line segment. And the line segment intersects the spheroid. And so the convex set is this little line segment, which we have here, correct? And we see that that is indeed a convex set. So there's another example of the intersection of convex sets. Here is the incredible result of alternating projection onto convex sets. And this is where we'll pick up here next time. Let me give you a little bit of teaser. There is an intersection of the convex sets, which is here. Our job is to get to any point in this intersection. You can think of this as a design problem. And the design problem is to design a signal or a system or whatever that obeys C1 and also obeys C2. So we want something in the intersection. And here is the remarkable result. If we start with any value and we project back and forth between the two convex sets, we always end up at a point in the intersection. If we alternately project back and forth between the convex sets, we always we always go as a fixed point. What does a fixed point mean? That's the end point of the iteration. We're always going to approach a point in the intersection of the two convex sets. This is important because if you're trying to design, for example, a signal that satisfies C2 and C1, and you know they're convex, and you can project among them, you can go back and forth, and you can be assured with 100% certainty that you will end up in your iteration at a point which is in the intersection of the convex sets. This is referred to as a fixed point, because once we get to this fixed point, it becomes idempotent, right? The projection of this fixed point here at the end onto C1 doesn't move. The projection onto C2 doesn't move. So we stay exactly the same. So the fixed point is idempotent, right, to both sets. It's idempotent to both sets. Now, the interesting thing is that this convergence is not always to the same point. If we were to start out, for example, at another point, say we were to start out with this point, and we projected onto the line, and then we would project onto the spheroid, we would come up with another fixed point. Now notice this fixed point, like this fixed point, is still on the intersection. So this would also satisfy the constraints between the two sets. Now the cool part is if you can show that there's only an intersection at a single point, in other words, the intersection of C1 and C2 is only a single point, then you will always converge to that endpoint no matter where you start, no matter what the initialization is. So that is a cool, I think, introduction to alternating projections onto convex sets. And the question, of course, is where is this applicable? Where can we use this? We'll find out examples very easily of signal extrapolation. We'll find out subpixel resolution, and we'll also find out applications in tomography. In other words, instead of using an inverse radon transform, you can literally use POCS in order to reconstruct an image. And we will talk about that next time. Is there any questions on this at all? Okay, next time we will address the homework, which was assigned also. Okay.
Dr. Marks, I wanted to talk to you about the homework.
Okay, let's do it.
So I had emailed you the question, you probably remember, about getting the coefficients. I'm still really confused on that. I don't really understand.
Okay. Okay. Here's the point. And by the way, this is anytime you write a book, you lament the way you did things. And I lament the way that I did things in the book on Fourier analysis. There's a few things I lament, and here is one of them. What I did was I derived, and all of our treatment in class was a derivation of a periodic signal in U1 and U2. Now, what I should have done is derived a periodic signal in T1 and T2. And I could have done that, but I didn't do that. The reason that I did this is it makes an easier transition into the sampling theorem, because the sampling theorem is the Fourier dual. But nevertheless, choosing this is, problematic. Now let's look at this here a second. If you had the same sort of signal, except it was in T1 and T2, well, that I'm not very good at my penny packing here, am I? If I did this in T1 and T2, how do you find the corresponding Fourier coefficients? One of the ways is to take a single tile of the periodic function. This extends from the one dimensions. And you Fourier transform it, right? And what you get in terms of the Fourier transform is you get a sequence of Dirac deltas in accordance to the Coulomb lemma. And these Fourier, the samples of this one of this single period gives you the Fourier coefficients. Is that okay? Unfortunately, I didn't present that to you. What I did is I gave you a periodic signal here. And in order to get the Fourier coefficients, what you have to do is you have to do an inverse Fourier transform in T1 and T2. And you also get the Fourier series coefficients by the inverse Fourier transform, just by duality. So the confusion, I believe, is the idea that I'm doing the Fourier series here. So we do an inverse Fourier transform to get to the Fourier series coefficients here, whereas a more intuitive approach, which again I lament not doing in the book, is to take a periodic signal in T1 and T2, Fourier transform it, and get the Fourier coefficients in the frequency domain. So I don't know if that clears things up.
Yeah. So in the problem that you did in the book, you use the function in the frequency domain, and it gives you what you have in the top right corner, but
Yes.
It's actually with M instead of T because you have the QM, right?
Yes.
So then why in the book did you find the inverse Fourier transform first? If you use the frequency domain for the coefficients.
Well, okay, which we didn't do in the book. It was the frequency domain. So the Fourier coefficients have to be found in the time domain. That's my point.
Okay.
And that's unfortunately that was not a good way to do it. I worked it in a Fourier dual sense, and my motivation was it was a simpler transition to the sampling theorem. But clearly, if I were to do it over again, I would do the time domain to the frequency domain, because I think that that's a source of confusion.
Okay, got it. Thank you.
Okay. Any other questions? Hearing none, I will bid you adieu. I don't know what adieu means. What's adieu mean?
I think it's just French for goodbye.
Okay, adieu.